All right, so I think we're going to try to get started. People come in late. They come in late. My name is Jeff Bonilla. I'm from Sasaki Associates, the architecture firm that's designing the new building on campus, or what will be the new building on campus. And we're here today to talk about the zero net energy and how we're going to achieve it and what it means. And to do that, we're going to have Jacob Knowles from VR+A, who is the engineering firm on the team, and he'll be presenting the project. So I'll hand it over to Jacob. We have 2 sign-on sheets. One will go up each side. You guys can just sign them out and put your name down. It'll help everybody else. So, and then just return them back down to the front at the end. Thank you, guys.
So how many people here are engineering students? So what kind of students are you guys then?
Environmental science.
All right. Anybody else? That's everybody? All right. Well, thank you all for joining us today. We are at least as excited about this project as you guys either are or hopefully will be once you see what we've got going on together. Bristol Community College has really been the driver on this, and we thank you for this opportunity. So, for those of you that aren't as familiar with the project, we just want to give you a little bit of background. Here's your campus, and in yellow is the location where the new building will be located, approximately, next to the main quad area. This is an old image. I don't want to offend the architectural team, but just to give you some broad idea of roughly what the building looks like, or will look like. And then looking at just the floor plan, you can start to see some of the program breakdown. And the building will include dental, medical, nursing, bio, chem. Am I missing anything? Those are the general categories. So it's a really exciting building in terms of what's going to be happening in it and the interaction between these different programs, which obviously I'm sure you're doing now, but hopefully this will continue to enhance that interaction and collaboration. So this is the first floor. You can see generally there are these 1, 2, and 3rd sort of blocks that make up the main program areas of the building. And then connecting those, this connective tissue, is the sort of 2-story atrium kind of space that will allow for student interaction, study space, smaller social events, things like that. And you can see here, this is now the 2nd floor stacked on top, and it's got those same sort of bars, and then this main open space in the center. So, when we started this project, it was not a zero net energy project. This was another good best practice, high performance lab building that was going to meet the programmatic needs, and as all labs do, usually, it's going to consume a fair amount of energy, but within reason. It was going to be, saving energy compared to code. It was going to be LEED Silver, good, solid, well-engineered, high-performance laboratory. Project went on hold, as most projects do, in the process of getting funding and all the approvals in place after the initial study was performed. And during that time, at least as far as I'm aware, Bristol Community College signed on to a goal of achieving carbon neutral operations by the year 2050. And very exciting. So that's an amazing goal. And so when the project came back to life, we were inspired and in a way directed by your goals as an institution to follow suit and up our game and really rethink everything we had done, not just on this project, but on all of our projects in the past. So first thing we had to do was see, well, how are we doing? So we modeled the energy consumption of the proposed design in the computer simulation software. Based on that analysis, we estimated that the new building would consume approximately as much electricity as the entire existing campus, and that it would consume as much gas as a large portion of the neighborhoods in the area. Obviously, we were not doing very well in meeting our new directive. So question is, we started with our high performance. How do we get to zero net energy, or how close can we get to zero net energy? And so we started a process of brainstorming ideas and also looking beyond our project to see what's going on in the country and in the world that can inspire us and provide us with some ideas. So as you can see, this is a world map of zero net energy or zero carbon buildings around the world of all different types, from a small home to a large institutional scale project. And we wanted to find buildings that were of a similar type and use. So we looked for lab or medical education type buildings. And we wanted to find ones that were similar in size, if ideally. But it turned out that really these, I believe 7, were really the only ones that in any way compared to what we were trying to do for your project. So we decided to figure out, well, what's unique about these buildings, and how were they achieving zero net energy or trying to target zero net energy. And you can see we made a matrix, and it's listed from smallest to largest. And here's your project, roughly in the middle. The interesting thing was, as we started to dig deeper into the data on these buildings, is that something that we'd seen on other building types, like high schools or residential or small commercial, with net zero energy or high performance buildings, there's some element of natural ventilation in the building design. And that's something that's near and dear to our heart that we're trying to push towards. But given the fact that we work on a lot of research and healthcare projects, it's often not on the agenda. But seeing that pattern that applies to non-healthcare, non-research type buildings, non-science buildings, still applied this natural ventilation, this passive design, using less mechanical systems and more of the natural environment to achieve the energy performance, was something that we could see was something that was carried through in these other buildings that we were looking at. In addition, the one challenge we realized was that not all of these buildings really matched up with what we're trying to achieve. So for example, all of these in red here are not built yet. All of these numbers here basically show next to no fume hoods in the building. So they're not really as chemistry intensive as the new project for your campus. And also, a lot of them we either don't know because they're not built yet, or we know have not quite achieved zero net energy. So if we're going to actually hit our goal, we're going to have to do things a little bit different. The one that came closest to matching our goals for this project is this one here, the Ohlone College. And it's actually a larger project than ours. It's 137,000 square feet, so almost 3 times the size. So we figured that was the one we should probably spend more time digging into to get more detail. So here's an image of that project. You can see it's a 2-story building with 4 wings, covered in PV, photovoltaic panels. They also have enthalpy wheel heat recovery, which is a heat recovery system for the air being supplied to the building, the ventilation air, and you recover the heat from the exhausted air. And then also using a ground source heat pump system, in this case a slinky coil configuration. You can see the breakdown of their program here. There's the first floor and second floor. And what's interesting to see about this is actually their energy intensive program, like the chemistry kind of spaces. Even though their building is larger than ours, the energy intensive program is actually quite similar in size to this project. The only problem is ventilation being a major driver of energy consumption in this type of building, in a climate like California with much more mild temperatures, means that we're going to have to go further. We're going to have to do even more, be more aggressive than what they have done. So we still are left with the question of how are we going to make this work? So we brainstormed. We came up with a series of different approaches. We worked with our cost estimator to do some initial feasibility assessment from a first cost perspective. We did energy modeling to see which option we thought might perform the best, and came up with roughly this scheme, which has continued to evolve to some degree. But what we want to do is spend a little time going through what are the key components of this new design that make it unique and make it meet our goals. So step number one, zero net energy building. Can it consume natural gas? By most people's definition, no. If you're consuming fossil fuels with your building, it's not a net zero energy building. So we cannot use our boilers anymore to heat our building. What are we going to do? So best option is a ground source heat pump. And essentially all that's doing is taking the heat that's in the ground, extracting it, and putting it in the building in the winter. And what's great about a heat pump is you can reverse it. So now it will also, in the summertime, extract the heat out of your building and pump it into the ground. It was critical for us to bring on an additional consultant for the project, geotech who specializes in ground source systems, Haley and Aldrich, and they've been an incredible ally in the process since they've been brought onto the team. There's also a huge precedent for ground source systems in the country, so we've been able to gain from that experience. Generally speaking, this is a diagram of the well field. So it's a series of vertical wells, 500 feet deep each. And the water that's being used to transfer that thermal energy back and forth between the building and the ground is actually in a completely closed system in sealed pipes that go down into the ground and then back up. And it's through conduction, through contact with the ground, that heat transfer occurs. So as I said, it reverses its process between the different seasons. And what that means ultimately is it's not that the ground is 55 degrees all year round, which would be maybe the case if you weren't pumping heat in and out of it. But what's actually happening is you start here in the fall. As you move into the winter time, you're pulling energy out of the earth to heat your building. So the ground is actually cooling down. And then you get into the spring, and now you need to cool your building. So now the fact that the ground has been cooled all winter by extracting heat out of it is an advantage. And you're then pumping your heat back into this nice cool ground as you're extracting heat out of your building as you move from spring into summer. And that cycle then occurs year after year, and it's critical to get that to balance so that your temperatures in the ground don't start to skew and shift out of our minimum and maximum temperature brackets that we want to maintain in the ground in order to achieve our energy performance and be able to maintain our capacity with our systems to handle the load for heating and cooling the building. What's interesting though is you see that this blue line is actually at 30 degrees Fahrenheit and the red line is at 90 degrees, which is hotter and colder than for a traditional ground source heat pump system. Now this has been done on a number of projects, but it's becoming a more common approach because instead of having 84 500-foot deep wells to get the capacity you need because you have a smaller temperature swing, when you can drive that temperature lower, you can extract more BTUs. You can pull it higher in the summer. You can reject more BTUs. And what that does for you is it takes us down to 25 wells. So it's a dramatic reduction at $25,000 a well in the cost of that system. Yes, you take a little bit of an energy penalty, but if you look at the overall investment from a life cycle cost perspective, this is an incredible advantage. In addition, we've handled the peak loads for both heating and cooling as a backup, basically, system with an air source heat pump. And basically, that's the same idea as the ground source heat pump, where it's pumping heat in and out, but instead of with the ground, it's doing it with the air. Now again, that's a little bit less efficient overall, but from a cost perspective, it's a dramatic savings. And overall, it's the optimal solution because you can use the ground source when it's best and then have the air source as a backup, or use the air source in the shoulder seasons when it's still cool out, but you need to be cooling the building. The air may actually be cooler and a better source of cooling your building than the ground is. So we've got this great opportunity to do the trade-off and balance and always be optimizing the efficiency of the system while not overspending on the dramatic cost of 85 ground source heat pump wells. So that then reduces our cooling consumption a little bit by being more efficient on cooling, but it dramatically reduces our heating consumption because we're not combusting fuel to make heat, which is at best approaching a 1-to-1 input to output ratio. We're pumping heat from one place to another. It's not like a toaster that's using electric resistance and it's taking all that electricity and trying to turn it directly into heat. It's just moving the BTUs from one place to another. So you get 350% efficiency out of it. It seems counterintuitive to get more than 100% efficiency, but that's the amazing advantage. And as we said before, you're not burning any fossil fuels anymore. Although one caveat, we do have an emergency backup boiler for if somebody goes with a baseball bat to our heat recovery chillers or something happens, we have a backup plan to not let the building freeze and the pipes burst and destroy your building. So we've got a backup just in case. But it's been dramatically reduced in its capacity compared to the original heating system. So here's the new building on the left proposed, and here's that 25 well field next to the building. You notice that that's right in your quad, right? So luckily, it's all buried. So when it's done, it'll be grass. You won't see anything, as you can see here. So that's step number one, just getting off the fossil fuels. I don't want to go completely over time here. How am I doing? 20 minutes? Okay. So step number two is we've gotten off of the fossil fuels, but we still have a building that's consuming too much energy. The size of the ground source system would have had to have been too big if we were using all once-through air in the lab spaces with all the fume hoods driving very high ventilation, exhaust and makeup air rates. So we're using an innovative technology that we've used on 2 past projects, and which has also been used on many, many projects for actually about 40 years now. But it's something that most people are not aware of, which is instead of ducting the fume hood to an exhaust system, you use a filtration system built right into the fume hood. You can see it here. These are the filter banks on top of the fume hood. And these are activated carbon filters that are specially designed to be able to capture a very broad array of chemicals that are typically used in chem, bio, any of the sort of uses that you would have for this building. And we've actually gotten chemical lists from all the departments and vetted them, and we'll continue to vet them as they maybe shift a little bit as the design is finished. But these filters are actually capturing the chemicals at a molecular level. It's not like a typical filter where a piece of dust hits a surface and is just caught by the fact that it's sort of bumping into an obstruction. They're literally sites that these molecules are within the carbon filter that they're attracted to the surface of the material, not because they're hitting it as an obstruction, but because the chemical bond is created and they're connected to the. Go ahead.
No.
Actually, feel free to interrupt me if you guys have questions. So not only is there's also a redundant layer of filters, and there's a whole sensing system in between the 2 layer filters, so that as the first filter becomes saturated and can no longer capture any more molecules, the sensors identify that, and you still have the backup filter with its full capacity. So you take out the old filter, you take the top filter, put it down as the new primary filter, and you put in a new secondary filter into the fume hood. And
with the old filters?
so they incinerate them to eliminate all the chemical content. There is energy consumption in the process of dealing with the filters, but what's interesting is that the filters are carbon. They come from, I think it's like the husks of coconut or something like that. They make it as carbon neutral a life cycle as possible. There is energy consumed in the transportation of them, in the manufacturing and the incineration process, but it's an order of magnitude smaller in terms of environmental impact than just using all this energy to run ducted fume hoods. In addition, these have been in place for 40 to 50 years with a slightly different filter technology that had to be tuned to specific chemical groups. And the more recent advancement is that they've been able to create a filter that doesn't need to be selected specifically for your acids or VOCs. It can be done for a very broad range of chemicals, which gives you a lot more sense of safety and flexibility. Again, there's many clients for these type of filters that are using these products. This one company has been the one in business for 40 to 50 years, and they supply thousands of these replacement filters around the world. So there's a lot of confidence that this is a long-term investment. Again, they filter out a wide array of chemical types. A big advantage of the filtered fume hoods, not only is there a reduction in the amount of air that needs to be brought in and rejected from the building, but now instead of having the ducted fume hood having to be exhausted out on a separate system that then can only be heat recovered from that using a less efficient heat recovery, now we can take our general just room exhaust for the making sure the room air is clean, and we can take that and exhaust it combined all together through an enthalpy wheel for heat recovery. An enthalpy wheel is basically what it sounds like. It's a wheel in the air handler, and it cuts between the incoming air and the outgoing air, and as it spins, it's transferring that thermal energy from one airstream back to the other. And because it's counterflow, it gets you better than halfway. Because the two airstreams are going opposite directions, the front face of the wheel on one side is where the air leaves on the other side. So it gets you past the halfway point to the energy recovery. So it's about 75% overall recovery, depending on your airflow balance. Because the air is room air, there's little concern about some sort of contamination or carryover, because people are in the room breathing that air. If it's that much of a problem, the carryover isn't your concern at that point. We've got over 10 million square feet just of our own projects using enthalpy wheels for heat recovery. So a lot of these technologies and strategies we're using are things that we've done many times before and have a long track record with, and we're just combining them in a new way and trying to optimize it as a whole system. Another component to this overall design is air acuity. This is a proprietary system, one of just a couple that we need to achieve this goal for the project. What it does is it actually has a network of tubes that draw air from all the chemical use areas in the building, bring it back to a central testing piece of equipment that then continuously is sucking a little bit of air from the exhaust of each of these chemistry labs and biolabs and so forth, testing that air and making sure that the air is safe. Now, that's a health advantage for the occupants, but in addition, it allows us to reduce the air change rates in those lab spaces because we have a greater confidence level that the air is safe. And then if it does happen to sense something, we ramp the air change rate back up to its higher design value to purge that air out to make sure that the occupants are safe. So again, all this idea of like, how do we get the air change rates down? How do we get these loads on the systems down? And again, long history for this type of technology, as well as typical air change rates are 6 air changes. And we're using 4 air changes occupied and 2 air changes unoccupied in these lab spaces. And that has a long history of precedent both in our own projects and in other projects around the country and around the world. There are even some that go 3 air changes occupied. There are some that are 2 air changes occupied. So this is close to the extreme, but there are even more extreme examples of reducing that airflow. Now we've gotten the airflow way down, right? Turn down the fume hoods, turn down the air change rates, monitoring the air quality. Now finally, the driver of what needs to be supplied to the space is the loads, the thermal loads, because you need to use that air to cool. So rather than using all air to cool down the space because of all the equipment that's in there and the people and the lights, we're using fan coil units, which you have many of throughout the campus currently, but the newer models are extremely efficient. The fans use very little energy and they can ramp up and down based on demand rather than just being constant. And so now our ventilation rates are just what we need for air changes and for ventilation. We've decoupled that from the need to handle the thermal load. It does provide some of the thermal capacity, but with the fan coil units much more efficiently achieve that because blowing a bunch of air is very energy intensive in terms of the fan energy because there's very little cooling capacity per volume of air. But the water in the pipe that goes to the fan coil units has much greater capacity in the order of magnitude of like 500 times per the volume to bring that cooling or heating to the space. And then you just blow air locally over the coils, which uses a lot less energy than trying to bring it all back to the air handler and refilter, retreat, redistribute all that air all over again from the main air handler. So again, fan cooling units, nothing new there, right? Just a good application for the project. Lighting, power density, and plug loads are another key driver here. So we want to keep reducing these loads through the lighting design. Our target now is a 50% reduction compared to the code allowance for lighting, which is an aggressive goal, but we're being very careful about all of our lighting designs and testing multiple options, doing actual lighting simulations to make sure we're getting the right amount of light on the surface in the space while minimizing the amount of electricity consumed. We're also doing a very detailed survey of the equipment loads so that we make sure that while we're reducing our design of our system in terms of capacity, we're not going too far. So we not only want to handle all of the equipment that's going to go into this building day one, but part of sustainability is the long-term flexibility and use of this building. So we're designing still to have extra capacity for the future depending on what new equipment might be needed. But part of that process is the right sizing and understanding what you're using now. So we've gone into some of the labs and we're continuing to finish up with the ones we haven't seen yet. This happens to be from the dental clinic. And you can see on the left, that's the main dental clinic space. There's their materials lab and there's the radiography. And then the breakdown of all the major equipment in those spaces. And then how many watts per square foot of cooling demand is going to be driven by that equipment. So this is very different. If you look at the nameplate on the piece of equipment and you look at the rated draw on the electrical side, it's dramatically higher than what you'd actually see in terms of load in the space for most equipment that's only on for a few minutes at a time, or maybe has a peak draw but then is not operating at that level, like for example the dental chairs. How many people sit in the dental chair and go up, down, up, down, up, down for an hour straight, right? Nobody. So you go up, you fix the back, and you leave it for 10, 15 minutes, maybe you adjust the back again a little bit. So we're taking all of that into account, metering things all at the individual equipment level as well as at the panel to be able to build a reasonable total as well as understand where those components of energy draw are coming from. And you can see on the left, the autoclaves in the dental clinic are a major driver of the need to cool the space. They consume a lot of electricity. They run actually for a while each, and they might have 6 on at a time, which was the case when we walked into the room. You can go over there and you feel the heat coming off of these things. So either putting them in a separate room or using the return air locally in that spot to actually pull some of that heat out of the space before the fan cooling units have to cool it all down. So we're looking at not just right sizing, but also looking for design opportunities by understanding the equipment and the program for the building. Another piece of this is we're expanding the temperature set points. Typically, we might design a building like this to be 70 degrees minimum and 74 degrees maximum. And you can always get it, no matter how hot it is or how cold it is, you can get it into that range, except for like a freak weather event. We're expanding that just by a couple degrees in each direction, and that has not only energy savings, but the capacity of the systems is reduced. And that's a big driver when you're looking at ground source heat pumps to be able to handle that load. A little bit bigger boiler is no big deal. Another well, that's expensive. So that's a key component to this. A lot of the time we will be able, occupants will have a plus or minus 2 degrees adjustment, and they'll be able to get it back to that 70 to 74 range. But when it's hot in the summer, it might be 76, for a few weeks in the space. And that's something we're still discussing with the whole owner team and making sure that that's acceptable and that overall we're meeting the needs for the building. Because if it doesn't perform for the users, then it doesn't matter how green the building is. But that's our process at least. Building envelope air tightness is also really key. There's a lot of leaky buildings being built in the industry, and you don't really know, right? And it's more than just an energy issue, which of course is a problem for a building like this, but it's also a moisture control issue, air quality control issue. So we've advocated beyond the ground source consultant, but to also have a piece of the construction contract where they'll do whole building blower door air infiltration testing to hold the contractor's feet to the fire during the construction process and make sure that they are meeting our air tightness requirements for the building. As you can see, there can be issues. On the opposite end of the spectrum from tight envelope, we're also integrating, as I said before, natural ventilation and passive strategies into the building. Not into the lab spaces themselves, because we have to maintain the pressure relationships at the fume hoods and in the room, but in the softer spaces in the building, like the main atrium. And so you can see here, this is the main atrium through the center. That's one space that'll be naturally ventilated when appropriate, not obviously in the winter or a peak summer day. And then also the dental clinic, the private offices, conference room, and you can see our scheme here is basically to have the wind, which often comes from the southwest in the summertime, come in through the end of the atrium so that the ends of the building help kind of scoop that air into the building. And then as it moves, toward the leeward side of the building, it's going to pick up some heat from the people, the lights, the people's laptops, whatever's in the space. It's going to make the air more buoyant, so it's want to go up, and it's going to want to go downwind. So we have operable windows also up here in the clerestory upper windows of the atrium space to sort of use that natural flow and optimize that. Along the lines of expanding the temperature ranges for the building, there's kind of two ways to think about thermal comfort. There's thermal comfort that people expect when they know that they're in a closed space like this and it's mechanically cooled and ventilated and heated. As a society and just psychologically, there have been studies that show that you expect that to be controlled. But when you are in a space where you can see outside through the window, you can change your attire. You could put on a sweater if you're a little cooler or take it off. You can have some control potentially over the natural ventilation by opening the window. That your psychological connection to the outdoors shifts your perception of comfort just a little bit, just a couple more degrees, where it's called the adaptive thermal comfort standard. It's still part of the same guidelines that we use for mechanically conditioned spaces, but these studies have shown that that range shifts, and not only does it shift in terms of being a little bit broader, but it also shifts throughout the year. So when it's cooler, like in the spring, your perceived comfort range is a little bit lower on the scale, and your perceived comfort actually shifts up to higher temperatures as you move into July and August. Number one, you're wearing different clothes probably, but also you're just more acclimated to that average temperature for that time of the year. I mean, imagine if you walked into a space that was 68 or 67 degrees on a 90-degree, August day, and you're sweaty and whatever. You walk in, you might get a chill, like going into a movie theater or something, or a cold restaurant in the middle of the summertime. So why overcool the space when you'd probably actually be more comfortable if it was a little bit warmer, within reason, right? So that's that sort of sliding scale of the adaptive thermal comfort. And we're not just using rules of thumb. We actually built a detailed airflow network model to analyze this and model it based on the current design, taking into account weather conditions, occupant schedules, equipment loads in the space, and so forth. And we took that and took opportunities in our analysis to test different ideas and look at, well, what if we extended the overhang on the east-facing windows on the high clerestory of the atrium? How many % of the people in that space would go from uncomfortable to comfortable? How much does that influence? So you can see here on the left-hand side, as you move down, there's less people that are dissatisfied with the thermal comfort. And as you move to the right, the overhang on that shade is getting deeper. And we're looking at 3 different spaces in that atrium and looking at not just that there's a benefit, but you can see how this curve kind of drops down and then it starts to plateau at a certain point where the shade isn't helping you anymore. So we don't want to spend a lot of money on a shade that's too deep. So finding that sweet spot is part of this testing and optimization process. And then we can also look at, so here's some of our recommendations for the design revisions. We can also look at what is it going to feel like in that space? What's going to be the perceived temperature? Because temperature is more than just like what the thermostat says. Temperature also takes into account the radiant temperature. So if the sun's hitting you, you're going to feel hotter near the window than the thermostat might read in the room. If it's really humid in a space, that's going to affect your perception of comfort. If the air is moving quickly, like if you have a fan blowing on you, or if it's stagnant, again, all these things affect your experience. So this graph represents the perceived temperature, taking into account all those factors. On the left-hand side, you can see those sort of representative temperatures going higher. And then as you move to the right, you're looking again at that adaptive effect of the average monthly temperature rising or falling. And this is the data from the model. It's also color-coded by month. So you can see it starts out low here in April. It rises in May, starts to spike in June, July, August, drops in September. There's a spike due to weather as well as some low-angle sun later in the season coming in, and then it drops, more deeply in October. Now, what's interesting about this is not the graph of the natural ventilation mode. This is the graph of it in mechanical operation, where the minimum temperature is sliding up through the months to follow that minimum on the graph, and the maximum is just fixed at 80 degrees. And what's interesting is you go from the mechanical only operation to using the windows to pre-cool the space at night, to bring in ventilation air, that when it happens to be cooler in the day, to provide some air motion to different regions in the space. And it's a dramatic improvement in thermal comfort. So using non-mechanical means to condition a space can actually make it more comfortable than using the mechanical systems, if you're using these expanded temperature ranges. So if you use a mechanical system to get it dead on every time and you just expend a ton of energy, okay, maybe that's more comfortable in theory. But to me, if we're looking at getting ourselves a little buffer on these temperatures, there's a dramatic benefit for energy and thermal comfort to use the natural ventilation. You can see the main difference here is on the right-hand side of the scale, those high temperatures, they're just sitting at 80 degrees week after week, hour after hour in the summertime because your system is only keeping it from getting hotter than that. Now you're taking advantage of the ability to pull that down with the operable windows. So beyond all of these strategies, again, we got to always come back to this building has to work. It has to work for 50, 80 years. It has to be flexible. It has to meet many more needs than just zero net energy. So we're providing that flexibility, that added capacity. We're doing it strategically. We're applying it to systems like the piping, which is cheap to add a little more capacity for the chilled water or hot water distribution through the building. And then if we need more capacity in the future, for example, at the heat recovery chiller plant, we'll leave us extra space. We won't buy the extra heat pump, but we will make sure that you have the flexibility down the road. All right, so we still don't know how we did, right? We came up with this great idea. We think it's going to save the world. Is it? I'd say we did pretty well. This is based on just an energy model. There's many more hurdles to go through. It's not built yet. It's not net zero energy yet. But we've eliminated, based on our energy modeling, we've eliminated the fossil fuel consumption. And at the same time, we've dramatically reduced the electricity consumption. So even though we're using electricity now to heat the building with the ground source system, we're still reducing the overall electricity consumption. In addition, I think we're helping to meet the college's goals of a sustainable infrastructure and a sustainable campus, not just one sustainable building. So the 2 megawatt PV array that's going to be installed on the parking lot will not be, as you see on the left, completely consumed or almost completely consumed by the new building. Granted, we will need a fair chunk of it because this is a lab-intensive building, and no matter how efficient you make it, it's going to use energy. But we've saved, luckily, a lot of the PV array to still feed back into the other buildings on campus. In addition, we're saving about $100,000 a year in energy cost. That's a lot of opportunity to spend that money on better things than just consuming energy. All right, the real test, right? So we've got zero net energy, we're saving money operationally. Can we afford it? Everybody thinks that most people think, that to get higher performance and save energy, you got to spend more. But fundamentally, what costs more to build, a house or a lab for the same square feet? A lab does, right? It's got more loads, it's got more air change rates. So it actually, the whole idea that you got to spend more to save more is completely backwards. You got to spend more to use more. So we looked at the side-by-side cost comparison. That was the great thing about this project going on hold and having one whole design that was up to a schematic design level with everything kind of laid out, and then having to restart from scratch. We've now got this great side-by-side comparison case study with detailed cost estimates. It came in lower. Not a lot, basically within the margin of error, roughly parallel, but we were pretty excited about that. I mean, this is not, it's unusual to have a zero net energy building. It's doubly unusual to have a zero net energy lab building. We haven't really found any. It's triply unusual to do it at no added cost. So to us, this changes our paradigm. We think this is going to be an amazing building for you guys. And I think it's going to be a game changer for the industry. So we thank you so much for this opportunity. We're really excited about it. So thank you guys. Yeah, does anybody have questions? Anything you want to review or? Yeah.
I have a question. Has anyone looked at maintenance costs and maintenance of all these?
Absolutely. So we did do a sort of a very preliminary life cycle cost comparison between the two, and actually it segues nicely. Took that into account in that looking at the costs of the systems as one of the factors for what they would cost to maintain them. And there's a little bit of a premium on the ground source system in terms of the heat recovery chillers because there's more of them. Other than that, really, there's savings in other areas, like the air handlers went from 74,000 CFM to 28,000 CFM. And so you look at the filter replacement, the fans, the motors, all of the components of those, and other systems in the building that are now smaller. And there's probably a small uptick in maintenance, maybe more because of unfamiliarity. And Leo is amazing. He's the guy who's going to make this all really come to life. But we took that into account in our life cycle cost analysis and came up with roughly a $1.5 million net present savings using this approach overall. Thanks. Anybody else?
You talked about air quality and temperature and all that. How is that all being monitored? Will we have thermostats? Is that how all that will get? Because again, I'm in fossil fuel mode, and I kind of look at mine. If it's 65, 70, I just go to the thermostat. How does that all? Is it all magical? How does it all happen?
Yeah. So the thermostats are applied in each zone, which is almost every space in the building has its own temperature control. And you can have some plus or minus to the standard set point for that zone. And the standard set point can also be shifted by the facility staff. But the really exciting thing about these thermostats is that the screen itself lights up a different color depending on whether you want to be, at least for the spaces with operable windows, will light up a different color to tell you when you want to be in natural ventilation mode or in mechanical conditioning mode. And so it'll tell you when you should open your window for the spaces where the windows are manually operated. In the atrium, the windows are on actuators that automatically open and close the windows based on the weather and whether it's going to be more energy efficient to use the windows or to close them. So does that answer your question in terms of it sounds like you were asking about can you adjust the temperature a little bit in the space?
Yeah, it sounds like the building's going to do it for me.
To some degree, yeah. But there will be some individual level of control. We're still working out, is it +2, -2, or is it +1, -1? And what is that starting point that it stays at automatically? And if you leave the space, does it reset to that standard? Or does it stay fixed at what you adjusted it to? So we're still working out some of those details.
Or even like windows opening
Yep.
How is that happening? Is that an electrical thing? Is it censored? Is it?
Yes, so there'll be a weather station on the roof. The weather station will take into account some of the weather data that the air handler outdoor air intakes can't take account for. For example, if it's a misty day, you might want to automatically close the windows so that you're not getting moisture on the surfaces in the building. The actuators on the windows are a very robust drive. It's almost like, it looks kind of like the chain on your bike, but it's thicker and more rigid. And it comes out of just a little kind of gray silver box that's mounted on the edge of the window where you'd normally have a crank or a handle. And it just, with a little motor, it drives that chain and it pushes out the bottom edge of that awning window. And then it closes it again. The great thing about these is they're actually used in critical building systems like smoke evacuation in buildings with very large atriums where you need to have smoke evac fans on the roof in case there's a fire because the upper levels can get flooded with smoke otherwise. And so the smoke evac fans will turn on, and to get air into the building to make up for that exhaust, the windows will open. And so we may not actually use like a UL rated unit, but we'll use one that has that same robust quality of something that's as reliable as something that life safety would depend on for operation. So these little units are really well engineered to make sure they'll continue to operate for the long haul. Right, and thank you. Just to clarify, it's just the atrium that is automatically operated, and it's just those other few spaces that we showed that have the manual windows. The chem labs, the bio labs, medical, nursing, education, those currently don't have operable windows, and certainly any space with a fume hood would not, because you can't control the pressure in the space, which is important for the fume hoods and chemical use.
Thank you.
On your high performance design, you said you were a LEED silver,
Yeah.
and now you're a net zero. Assuming that you stayed LEED silver, what are you now with this net zero? It must be platinum.
Yeah, we were actually just talking about that today and went through the whole LEED checklist, and we're at about 85 points and maybe 88 points depending on some of the site credits. And so yeah, we have a good buffer on getting platinum.
We've been having emergency drills on all our campuses, lockdown, shelter in place, and one of the campuses has had an active shooter drill. Is this building going to be safe in terms of that type of safety and security?
I would say I wouldn't say we're designed specifically for that type of security, but I mean, we had talked about installing card readers on the buildings for access at certain times. I mean, this will also have a dental hygiene clinic. So because that clinic, it will be open to the public. It's not going to be a completely locked down building because of the fact that it has to be accessed by the public. But at night time when that clinic isn't open, there's definitely going to be card readers. Also, a lot of those labs can have card readers. We've talked about it, discussed it for events that are just a key lock system. Overall, I think safety is definitely a concern. I know the campus has taken safety to a concern with cameras and other things associated, and we've talked about what to do about in our atrium or around the building. I don't know if it's been addressed specifically for what you just said, but I mean, I think overall security is a concern with any building we design.
All right. Thank you, everybody, for joining us. We're happy to stick around if you have any more questions.